On in the 1980s and right up to today, really. So today, surprisingly to myself, we find ourselves one of the largest copper-based foundry groups in Europe, and certainly the biggest in the UK, with around 350 employees. But it started with quite modest beginnings. The slide at the bottom there was taken in the 1930s, and the chap on the in the little circle, the bottom right, is my father, and his brother, and my grandfather behind. That was the scale of what they were doing in the 1930s. So, I'm just going to this because I hope it sets the context for how we became involved with bell casting, which I shall come to in due course, so bear with me. And I did an exercise a little while ago just to see, going back to the 1982 was our first proper acquisition, you could say. And there's a list there in that box of all those foundries which are currently represented by what Westley Group do today on just 4 sites. There's 33 foundries there. Some quite famous names of engineering companies: Yarrow Shipbuilders, Devonport, Swan Hunter, Hamworthy for the pumps. You know, amazing diversity of who actually decided to close the foundry and pass it over to someone else who could perhaps do it more commercially effectively. So, to come right up to date, and just to give you a sense of what we do, these are what we do on these different sites. I say we have 4 sites today. So on the original Cradley Heath site, close to Birmingham, we specialise entirely in centrifugal cast product. That's making cylindrical shapes, but it's exclusively copper-based and nickel-based alloys. We do a little bit of engine trim for Rolls-Royce with some special irons and steels, but it's principally copper-based and nickel-based alloy cast parts. And the applications of that are completely global. This business exports 80% of what it produces, and typically most of that finds its way into marine propulsion systems. Everything from cruise liners, submarines, merchant ships, everything that's got a big bearing that is exposed to seawater. That's what we do at Cradley Heath. This is the Holditch Road site, which is in Newcastle under Lyme, and this is where we actually, this is a site where we do the bells. But this is really set out, there's over 100 employees on this site, to make, again, engineering castings principally. So you've got pump and valve parts. We will make the frame around which is an aluminium casting, around which the body scanners are built. So it's quite a big casting, the person can fit inside there. We've got a semi-automated carousel plant where we can do some quite repetitive work. We tend to be bespoke, but we do some repetitive work, and we make some very large marine components in the top right-hand corner there. That is half of a bearing shell for a nuclear-powered icebreaker for the US Coast Guard. Now this is an extension of the products that we do on this road, and this is based around sand casting, same size, and this is just an example of many of the works of art that we do. This is Damien Hirst in the bottom left corner here. Kate Moss, you might recognise her, that's strange. and then Portcullis House. Increasingly, we're making, because of the desire to build new structures that are properly sustainable, the design brief to when the government commissioned the construction of Portcullis House to the architect was that it got to last 1,000 years. And it was quite cleverly done, it was very clever, because it is exclusively built out of stone and bronze on the outside. So the maintenance is zero. There's much fuss in all the national press about how much it was costing, but actually, if it's going to last 1,000 years, that's not a bad deal. And then in the far corner, you will have spotted a bell. That's one of the early ones that we made, and that chap standing behind it, and his dear wife, is Terry, who's now founding director there. So this is our other site in Stoke, which basically focuses on high integrity marine parts. And all those parts there are for the, top and the one in the top right corner, are for the UK defence market. They're principally parts for submarines. They contain the water cooling system that cool the reactor. The other site is Cleckheaton in West Yorkshire, specialises in firefighting equipment. That grew out of a business which we acquired, which made all parts that go on sort of standard fire engine. Did a lot of work in the Second World War, making a lot of these parts out of aluminium as well as bronze to make the bits that go on even petrol tankers and things that share the same technology. But that's a good business in that it's finished with a product. A lot of those parts are used in the offshore oil industry, and we recently completed the project doing many of the valves on the Crossrail in London. So here we are, bell casting. The ancient history of bell founding has been very fascinating for me to research. I'm a chartered engineer by training and a metallurgist, and I knew of bell. In fact, I was at Imperial College many years ago, and I remember going on a company visit to Whitechapel Bell Foundry when I'm well more than 40 years ago, thinking that's fascinating, and never imagined that one day we might get involved directly. So anyway, the way the bells have been made, as you well know, has got a long tradition of heritage and what has been done, and with variable levels of success. I mean, there have been some fantastic bells made, which everybody must be greatly impressed by, but there have also been some pretty good disasters and everything in between. So the whole idea, when I decided to become involved, and Alan Hughes kindly helped us in every way to share the shapes and designs and technologies that Whitechapel had accumulated, we thought, let's look at this as if it were an engineering casting, that we're trying to make the best that can be done, and let's take that as a starting point for how we would design it, and not worry too much about how you used to do it, apart from the shape. So, you don't need me to tell you, but Whitechapel have got a fantastic back catalogue of work that's been done, and I'm quite rightly very proud of it. So what I think is fascinating about casting as a process as an engineer is that it's quite unique in many ways compared to other engineering systems, in that it all happens in a very condensed period of time. So when you're actually going to pour this mould, everything has to be ready simultaneously. That's to say, the mould has to be perfectly prepared and clean and ready. Your metal has to be at the right temperature, it has to be precisely the right composition. You should have a gas content as little as possible, because molten metals absorb gas, and particularly copper-based alloys. Copper can dissolve 7 times its own volume of hydrogen, which is pretty shocking how easily the metal can become gassed. And then, of course, the pouring technique itself in order to introduce that. But all of this has to be optimized for those few minutes when the pour actually takes place. So there's quite a lot you've got to go into that to make it all come together. So, reiterating here, high integrity engineering castings are our forte. It was my view that Whitechapel Bell Foundry has got a fantastic history and reputation, and as we know, is Britain's oldest manufacturing company. So that, I think, is a unique and marvellous opportunity for us to build on this and try and properly inject into it the 21st century world-class casting technology, which is never going to be possible on the old site and in the old way of doing things. So we have this license in place now in Whitechapel, and we're trying to take full advantage of everything we can bring to it to make a better product. So the design and the shape are crucial, and we're very lucky that Nigel Taylor is working with us and extremely helpful to help interpret all these designs, and the back catalogue of shapes and sizes that we've got is as good as it gets, so we can use all that at our disposal to create bespoke parts that people want. Similarly with the mould materials, the decorations and dedications, all these requirements are unique for each bell. And because we're just a foundry, in inverted commas, we're not actually completely strapped to a particular brand of thing. I don't mind being a contract caster for other people's bells. You know, we in fact made a bell, one of our early ones, for Worcester Cathedral, where it was an augmentation to the existing ring, and they wanted it the same shape as the Taylor bell, with some of the particular features, and we were quite happy to do that. None of this is patented or exclusive, it is about making the cast part. But our constant theme is simply to make the most dense and highest integrity part, and exploit all that we can to do that. So, what makes the best casting? Well, no dissolved gas, no shrinkage voids in the metal after it's solidified, no insoluble particulates, no oxide films floating around, no contaminants in the way of other metals, and lead and aluminium particularly disastrous, even in tiny quantities, and a very precise control of the chemical composition is crucial, because the compositing ratio is vital to what the sound the bell will make, and will vary according to the proportions of the bell. We've got to make sure the bell is a casting that's physically and mechanically strong enough as well as everything else. Quiescent filling of the mould cavity is something which is vital, and that's something which has been developed by foundries and ourselves particularly since the 1980s and 90s, since computerized simulation of pouring has been possible, because the capacity of the computer systems now, and the data they can process, you can actually simulate what some of these poured reactions are.
Explain on quiescent. Sorry, what do you mean by that?
So with very little turbulence.
Oh, right.
So we pour them as it goes to the bottom of the mould cavity and then rises very quietly, I think, rather than just sloshing it in for the top and hoping for the best. Yeah, quiescent just means nice and gently filled with no turbulence. So this digital certification modelling is extremely helpful tool, and it's only been possible, I'd say, since the computing power has enabled it to be developed. And then the other thing is the mould structure themselves. These days, moulding materials is much more clever. There's lots of different sands we can use. We can use chromite sands, we can use zircon sands, we can use silica sands, and all sorts of polymer-based binders which are very much more robust than the traditional ways that the sands have been used in the past. And it can be recycled these days as well. They're engineered so they can be recycled too. So, how is this control achieved? Well, the first thing to say is all of our metal is melted electrically, induction furnaces, so you don't have the propensity to absorb gases from the fossil fuels that you're using to melt metal, because it's a completely inert environment. We can do reduced pressure gas testing, because we take a little sample out of the thing and put a reduced pressure and you can see if there's dissolved gas in the metal, because you'll see it will spit, and you can make sure by purging, we use dry nitrogen purging, you can take the gas content right down to very little. The latest spectrometry is what's necessary to control the composition, and again, because of the fantastic speed of computers and that you can strike an arc on it within a matter of seconds, you can have a precise composition. So that this all can happen in real time and is very, very complementary to getting it right. Engineered running and feeding systems we've already talked about, as well as computer simulation. But this is the sort of investment that it's almost impossible to justify in a normal bell foundry. So going on from that, we were involved in the 90s with Professor Campbell. He was the main materials man at Birmingham University. And the development of the computerized modelling was something which we did in parallel with them. They they set up a casting centre at Birmingham University, which we used to share with Jaguar cars, and it was to develop castings in a way that enabled us to fill the moulds in this quiescent way and to predict where the shrinkage would occur. And the whole of that process was an iterative one, so that we continued to develop our processes and develop the software. And the company now, which has sort of come out of it, is called Magnasoft, and they're based actually in Sweden, but they are the world's most respected builders of the software that does all this modelling for people making castings. Our methoding engineers are similarly been involved in the process all the way through, so we've got a deep-rooted knowledge base that has been at the leading edge of developing these systems. And then latterly, and this has tended to come in the last sort of 15 years, the pattern making equipment and using 3D CAD and additive manufacturing techniques are all really coming to the fore now, particularly on the pattern making side, and it really helps. So, metallurgy, for a little brief exploration of that. You can see the phase diagram there on the right hand side, and between those two red lines is the composition that most bells are made. They're really, it's just two different elemental metals, but the alloys are incredibly complex. There are a lot of eutectoids created, and they all mix together, so you've got a very, very long freezing range, from the point that it first goes from liquid to solid to the point when it's finally frozen off. It starts up there somewhere about 950 degrees and doesn't finish being solid until you're right down beneath 300 degrees. And what that means is all those complex eutectoids are freezing out and pushing into each other, and they lock into each other at the grain boundaries. So there is the reason metals are ductile is because the grain boundaries normally are flexible. You can bend a piece of steel and the atoms will hop around the grain boundary. Well, these grain boundaries are locked up because of the way the eutectoids have gone. And the good news about them being locked up is they won't be ductile. There will be very little damping capacity. They'll be hard and they will vibrate. And that's why bells behave as they do. They will continue to vibrate and will not absorb the energy that you put into them. And that's what gives them their distinctive and makes them absolutely fit the purpose for this job. So yeah, I would say earlier I was trained as a metallurgist, so I'm enjoying sort of learning more about this. And these ways that we look under a microscope now, you can see quite readily what the grain size is, what the grain boundaries are doing, and it's been an interesting piece of science to see how it all works. So, the reason why we don't want defects in these castings is because it causes a lot of problems. It is defects on a microscopic scale that cause nucleation sites for cracks and defects to develop. And the elimination of these nucleation sites can only be achieved by having what we describe as clean metal. That means, as I said earlier, there's no oxides, no particulates, no gas pores, just very clean metal. And a lot of this has come to be recognised, quite frankly, only in the last 50 to 60 years. Steels now that are used in car engines, in the crankshafts, or the central shaft that goes through the middle of a modern jet engine, they will be melted 3 times before you get to the bottom. And they're melted for those 3 times under vacuum to do all these things I'm talking about, to take all the bad things away. So it's going to be, and that doesn't make a bit of a difference to its lifespan. The fatigue lives are extended by orders of magnitude. It can be 100, 1,000 times longer. When the last time you had a broken crankshaft in a motor car engine, it's because the metal is so clean and really, really clever stuff. We don't actually cast them under vacuum, but we do cast under inert gases to try and eliminate any oxidizing potential from the air. So, some rumours and untruths. It's not true that bells deteriorate over time. A properly designed bell, when struck with an appropriate clapper, will be working well within its elastic limits, and the stress level should be so tiny that they will never induce fatigue failure. Bells that have broken in the past have invariably had some sort of defect in them, or they've been machined excessively so that they've been weakened. If the thing is designed properly, it'll last forever. So saying they are massively over-designed, and we take care to make sure, consistent with trying to make the right note, but they're also got the right mechanical properties to be. And weight actually is not an issue in a bell as it is with motor cars or aeroplanes. You just design something that's going to make the right noise and will be strong enough. The correct shape bell to produce the correct note should absolutely have enough bass to last forever, as I say. So, some facts, we call this. Horsehair and muxans were okay 100 years ago. I honestly believe there are much cleverer ways to make these things. And with well-vented and detailed molds, we really can move things forward. The digitally driven pattern making things we've spoken about. Perfectly round castings is another very important thing. It's crucial that the molds are really stable. Clean metal we've already discussed is key. And our skilled craftsmen, because it is still a craft industry, we do these on a one-off bespoke basis. The mixture of the crafts and the people and the technologies are what makes it all come together. So, some thanks. Like Alan and Catherine Hughes have been extremely supportive throughout the whole exercise of moving the production of these tower bells to our Stoke foundry. Nigel has been hugely helpful, a massive contribution to try and preserve all of the Whitechapel legacy in terms of the bell designs and how to improve the tuning process. And we've done that really by working very closely with Whites and Appleton, Brian White particularly. The close cooperation again to try and make sure there's no gaps between us and the starting point, which is a good casting, and then the finished working tower bell. And then Terry King, who's our founder director at Western and Me site in Newcastle under Lyme. But if you like, we're not trying to be all things to all men. What we're trying to do in Western is produce the best possible casting. And then we assemble a team of people, Nigel at the front end and all the designs, and at the back end, White and all that, so we can bring the whole thing to the best people, most competent to do all elements of the design along the way. So, future developments, I am learning personally, a very steep learning curve, and it's been really interesting just how emotive the whole matter of bells is in society. They're highly valued by communities they serve, and loads of passionate ringers, which I'm sure I don't need to explain, and then bells and clocks have often formed the centrepiece of human communities, not necessarily for ecclesiastical uses, but also just for purely somewhere to bring humanity together to do different things. And they're all engineered for their own purposes to produce characteristic sounds and shapes, but our ambition is to respect the human history and the legacy that binds all that together. So we intend to respect all these traditions. We would like to try and fire up the imagination of architects and town planners so that they can exploit what we would describe as high-tech bells, not necessarily in the church environment, but to just form the centre of communities. And the most famous bells are absolutely perceived by people as crucial to our society. So, thank you very much for listening to me on about it. As I say, I'm learning a lot about this and feel very privileged to be able to protect the unique heritage of Whitechapel bells and to be able to explain some of our philosophy to you today. So, I'm very happy to take questions if anybody's interested to ask any more about it.
Yes, I wondered if you could describe, when you say digital mould making, what the actual process or how mould is actually made,
Right.
sand or whatever, for
Well,
casting
what we do is we,
sunbells.
yeah, what we do is we create a pattern which the sand is moulded against, and it's in the creation of the pattern that we use all this 3D technology, if you like. So all these embellishments that go around the rims of bells, the Whitechapel logo, they're all now captured digitally, and we can recreate them at any size and any scale just to fit perfectly. And if we've got to fit perfectly around a particular diameter, the computer does all this cleverness, and then it creates that which we can stick onto the wooden pattern, which is similarly the shape of that. Again, Nigel can draw it out, but it gets into the computer, and then the pattern is, which is what we're going to use, is created using 5-axis, 3-axis, 4-axis machinery, which will create that perfect shape for us.
What sort of machinery or material? It's a machine that sort of makes some sort of mold.
Well, the machine makes the pattern, what we call the pattern, which is the piece which is going to look, it's the piece that's got the positive, that's going to look the same as the bell casting does. And then we put the sand around that to create the mould. Then the pattern is stripped away from the mould, and that leaves the void negative, which we can pour the mould right into. So, okay. I probably wasn't explaining very well to begin with. Yeah. Lady right at the back there.
Fascinating talk, thanks Tom, really interesting. You didn't talk about, I don't really know anything about boundaries really, but do you control the rate of cooling? Presumably if you slow down how quickly the metal cools, you're more likely to have close to single crystalline material, is that right? Bigger crystals, is that a good thing or a bad thing?
Right. It's very, in a sand casting, the sand itself will determine the rate of heat abstraction, and it doesn't matter if it were only because of the insulative nature of sand. If it were only 4 or 5 inches thick, it would have an extremely insulating impact. So the rate of heat dissipation through the mould is very slow. So when you put the molten metal into the mould, that's when it first hits the relatively very cold surfaces of the mould. And in the case of small bells, think of small castings in general, with relatively thin wall, that initial, shall we say, skin of metal that goes on there has quite a high chilled rate. And we believe, and bell fans that I've spoken with, believe that that's important from the perspective of having a nice fine structure on the outside of the bell itself. After then, because the rate of cooling is as slow as it is, it will become marginally slower, the rate of abstraction, and therefore the grain size should become marginally larger. But I think the differences are very slight, to be honest. I think there is a real benefit in not cutting the outside surface of particularly the external surface of a bell, and that's generally not done because you preserve that nice dense external surface. But it's only when you get to very, very large bells that you would start to consider how much sand you would put around it. And we have cast some quite large bells, and we've got some very large sand castings in general. And all we would do is then we would scale up the size of the moulding box, the flask of sand that goes around it, in order that it doesn't all come up to the same temperature too quickly. We have, with different engineering castings, we have in the past experimented with purposely cooling the outside of the mould flask to get a steeper temperature gradient. But that is much more benefit to other sorts of alloys that have got a short freezing. The long freezing range alloys are very happy cooling down slowly, and you get the best results doing just what we do. Yeah.
Is there an optimum temperature for casting bells, or does it vary on the size of the bell?
It does vary on the size of the bell, but there is absolutely an optimum temperature for each, because you want the least amount of heat above the liquidus to get the metal in there. Because the longer it stops molten, the more propensity there is, the more time there is for it to absorb other gases or anything that's going to cause a problem.
Are there any more different alloys that you might be interested in exploring to see whether you can cast a bell differently to that.
Good question, yeah.
Past.
We have, in the past, experimented with that a little bit. In particular, nickel aluminium bronze, which is a material used for its corrosion properties, is really, really strong. It's almost the strength of mild steel, and yet it has a lot of bronze characteristics. So you could, theoretically, make a very large bell that could be a lot thinner than a conventional one would have to be. Quite what that would do to the sound is something which we're exploring and playing with at the moment. But it does give you the potential to make a large bell with a much less wall thickness, if that was an advantage.
Can you tell us about any projects that you're currently working on or that you've recently completed, Bell?
Yeah, we've in the last 12 months we've cast more than 60 tower bells. We made our first ring, which was for Linfield in Sussex, which is now commissioned. And I'm pleased to say all the reports coming back are that they really like it, the guys that are involved. We've done augmentation projects where, as I said earlier, we've made bells that are bespoke in a particular shape to fit in with others. And at the moment we are, with Nigel, we're continuing to experiment with some of the fine-tuning, if you like, of the wall thickness in different parts of the, because I'm very interested in lecture earlier, Bill. There's a lot of research that it has been done, but there's a lot that hasn't been done, and there's a lot of stuff that's done because that's the way they always did it. And I think there's a bit of scope for a bit more science in how you can play with the, should we say, the dimensional design of the thing to achieve, and that's an ongoing experiment for us. Yeah. But most of our customers, to be honest, know what they want. They want one that looks exactly like that, or one that's, I'm not going to argue with that. But I'm not saying we couldn't develop something over time. We're saying, well, we've tried to optimise everything and listen to it and see what you think.
Might be an odd question, this. So, your firm has specialised in high-tech castings for submarines and crankshafts and things, but and so bells are new for you.
Absolutely.
Are you finding how are your staff reacting to making bells? Are they? Is it an emotional thing for them?
It's a great question. I would say my commercial staff thought I'd gone mad. What's this all about? How can I take this to the next bit and look sensible? Yeah, that's the higher ups. Everybody that works for me, and they're lovely people, all of them, and they're craft people, love it. Absolutely love it. Isn't that interesting? So I think the whole thing has got a sense of enthusiasm and passion, which I could never have imagined. And not just from our own people, but rather the people who want to come and see them being poured, and, oh, isn't this interesting? Can you tell that? So it's been really interesting, because for some reason, bells are an emotive subject.
The follow-on question, have you found your bell ringing customers a little bit more demanding than perhaps other commercial?
Well, they're all very difficult in their own way. I would say that the likes of Rolls-Royce are driving bonkers through technical stuff. And then the likes of Damien Hirst and Tracy Emin will drive me bonkers through their idea of what they're trying to do. And Bell people have an idea of what they're trying to do. So you just have to listen.
Is Brexit going to be a challenge for you?
It's a considerable pain at the bottom for us, yes, because we export more than 90% of what we do is exported either directly or indirectly. So it's not helpful.
You said you had 4 sites. Do you cast the bells at one particular site?
We do, exclusively at the Holditch Road site, which is the Newcastle under the line. And the other foundry that we've got in Stoke is just only about half a mile away, but that is almost exclusively devoted to nickel, aluminium, bronze and submarine parts. We did toy with the idea at an early stage of doing it all on one site and doing some expansion of our buildings, but to be honest, I think there was 2 things. First of all, we've been very lucky with the level of artwork that's going on internationally anyway. That's been very strong recently. And also, I think the segregation of some of the defence products is probably more helpful to my credibility to the MOD than would be if we were doing it all on the same site.
Do you suspect that at some point in the future you might add Taylors of Loughborough to that?
I have no ambition. I look, I admire what people do, and I'm not here to criticise anyone. We've all got really interesting histories and heritage, and as long as Taylors do it, that's absolutely great. But I do think that if you look at how the world develops, it tends to be that it becomes increasingly difficult commercially. The sort of level of investment that was needed to create these facilities, you couldn't possibly go away and say, we're going to the Bank of Ireland by several £1 million who's going to make a few bells every month. There's no way.
Are you talking to Loughborough?
Well, in a friendly way, not nothing other than isn't it nice making bells?
Suggesting any sort of
No, I've had a conversation this morning saying, isn't it great making bells?
Who does that about the tuning? Who does the tuning?
Nigel Taylor, and it's done at White's of Appleton. Because the equipment that was used at Whitechapel Strand in London, rather moving into our machine shops, which are very much engineering oriented, we moved them into Whitechapel, into White's of Appleton's premises, because it's just that much easier to control than to do it on site then.
I've got a follow-up.
Yeah, please.
Presumably, one of the other firms could tune one of your castings if the customer wanted them to.
We could, indeed,
But there's no reason why it has to be done by Whites.
Yeah, that's true. We started by working with Whites for the simple reason there'd always been a good cooperation between Whitechapel and Whites. And so we wanted to support each other, really, to make it a success. And I think, to a large degree, that has happened. And I suppose, to such a degree, in fact, the Whites are extremely busy at the moment, and we've agreed as gentlemen that actually we can make some bells for other people. Nobody's going to get upset.
If one wanted a bell tuned in Somerset, for example, then
yeah,
it's
fine.
possible.
Absolutely fine.
So, presumably you can make bells to different profiles. So if somebody came along and said, we want a Gillette profile, you can do all
That's
that.
exactly what we endeavour to do. I use the analogy, because we've made castings for pump and valve makers for 100 years, and if you go back in time 30, 40, 50 years ago, they all had their own founder, they all thought they could do it, and nobody does now. So we effectively become a contract casting service, really. Right.
Yeah, are you slightly concerned that seeing as some of Whitechapel's most famous bells seem to be slightly flawed, they seem to be cracked, that your process is going to be so perfect that you won't be producing any famous bells anymore?
That'd be a good outcome, I think, wouldn't it?
Yeah.
What's the largest thing you've ever cast? Not just bells, but what's the very smallest?
Oh, the largest we've poured in one go is probably about 15 tons in nickel aluminium bronze, and those are the propeller shaft liners for.
Those are the biggest things they cast.
And that was 1/2 of one bearing for that nuclear powered icebreaker.
Still less weight than the bell hanging in support.
Yeah, no, that's absolutely right. And that doesn't mean to say that we couldn't go more than that, by the way, because you get holding furnaces now, and that's what we do. That's been the sum of the induction furnaces that we could melt it in one blast. Right? But if you want to make something bigger than that, you can put metal into a holding furnace and go higher than that. We haven't had the need of that.
And the smallest thing?
Oh, some of the things we make are quite tiny on the carousel there. Little gears and bits that would go into a small valve. Wow, very few pound, less than a few grams. Okay, well otherwise thank you very much.